Hi, I'm Chenjun Wang. Today, I will present our ICIP work, Adaptive Voxelization for Transform Coding of 3D Gaussian Splatting data, with Shashank, Eduardo, Antonio, and Chen. We proposed a novel compression framework for 3D Gaussian Splatting data that leverages traditional point cloud compression techniques. I will first introduce the 3D Gaussian Splatting and the state-of-the-art 3DGS compression method, then talk about the proposed voxelization method and our compression pipeline. Finally, I will briefly talk about our experimental result and future work. 3D Gaussian Splatting is a learning-based explicit radiance field that offers faster training and rendering speed over a neural-based approach. Instead of representing the scene as a continuous function requiring a neural network, 3DGS explicitly models 3D points as Gaussian ellipsoid, with properties such as view-dependent color and opacity. The 3DGS is training using a set of images and optimized to minimize the difference between the rendered images and the ground truth images. The loss function ensures the model can generalize well when we evaluate on a novel test view, so the test image size is different from the training size. And 3DGS data consists of a list of Gaussians with a 3D position, 4D rotation quadridian to represent the Gaussian orientation, and 3D scaling factor to represent the Gaussian size. And we also have 48-dimension SH coefficient to represent the view-dependent color with 3D low frequency and 45D high frequency. And one-dimension opacity serves as a way to calculate the average pixel value using the alpha blending. We view a 3D Gaussian model as a 3D point cloud with multiple types of attributes and utilize the geometry-based point cloud compression techniques to compress 3DGS. However, a point cloud codec requires 3D point cloud to be voxelized. So we implement the voxelization of 3DGS data before compression. Existing work on 3DGS compression can be classified into generative and post-training and our hybrid method. The generative compression aims to reduce the memory footprint by producing lightweight 3DGS model through entropy-constrained training and removal of redundant Gaussian. Although the generative compression achieves a significant reduction in memory while preserving the rendering quality, it requires retraining a different model for each bitrate, which can be impractical for some application for real-time streaming. The post-training method takes an existing pre-trained model and compress it without any training. It compresses 3DGS model at multiple bitrate. However, the relatively small distortion in 3DGS parameters can lead to a large distortion during rendering, like a slight displacement of a large opaque Gaussian can induce substantial rendering distortion, as it contributes disproportionately to the scene and influence many camera views. Our proposed codec combines the strengths of both generative and post-training compression, enabling us to achieve a high rendering quality while preserve the multi-RD points. In order to avoid the Gaussian displacement caused by the voxelization, we do a lightweight fine-tuning on covariance, color, opacity to recover the rendering quality of the voxelized model. Then we can run the GPCC to compress the model at multiple bitrate. Here, we explain the uniform voxelization for 3DGS by analogy to 2D space and set up the partition depth to 4 here. Actually, in traditional point cloud compression, we uniformly partition 3D space into voxels and quantize the points to the voxel center, average their attributes. But the 3D point cloud from the volumetric dataset have a dense point distribution, while the 3DGS has a sparse distribution with irregular spatial distribution. Like for some local region, they are very dense small Gaussian. For some local regions, they are very sparse large Gaussian. In uniform voxelization, and another thing that the 3D point cloud, each point contribute equally to the render images, but in 3D-GS, a large Gaussian contributes more than the small Gaussian because they influence a larger region in render images. In uniform voxelization, such as used in GPCC, all regions of space are given the same resolution determined by the maximum depth of octree. Thus, the uniform voxelization can introduce large error by producing the displacement. And also spending too much bitrate on some dense region containing unimportant small Gaussian. Like here, we voxelize the 3D-GS model with different partition depths and render it. For the typical 3D-GS trained from tank and temple dataset, which has extremely irregular spatial data distribution, the object, like here, these render images, the object cannot reconstruct as well as the background. Because on the train body, tons of Gaussian concentrate there, and they just get deleted because they use the same 3D resolution as the background. And the background, they just have some sparse large Gaussian. In conclusion, the uniform voxelization is efficient if points are uniformly distributed, but become inefficient for the regions with non-uniform point density. Additionally, uniform method only considers the point position, but not the distribution or the size of Gaussian, thus ignoring the relative importance of Gaussian for rendering. To address these challenges, we propose adaptive voxelization for 3D-GS data, which can consider both the global data distribution and the local Gaussian importance. It selects a higher resolution for region containing higher volume, large volume, or the region with higher quantization error. And it adjusts to the lower resolution for the region with dense unimportant Gaussian. And here we set up a series of criteria for adaptive method to adaptively adjust the resolution for different regions. Here we use a two-Wasserton distance to determine whether to increase the resolution or not. Specifically, we compute the W2 distance between each Gaussian inside the voxel and the Gaussian at the voxel center. If the average W2 distance is too large, we further partition the voxel to increase the local resolution. However, due to the high computational cost of the algorithm, we propose another simplified version. In the simplified version, we first compute the volume. The larger 20% Gaussian are represented as the highest resolution at all time, J high. The remaining Gaussian are voxelized uniformly at the initial partition depth J low. Beyond these depths, further partitioning is determined based on the number of Gaussian within a voxel and their distance to the voxel center. If a voxel at a given depth contains a lot of Gaussian, indicating the need for further partitioning, and if the number of Gaussian is smaller than the partition depth, than the threshold, we will test each Gaussian, the quantization error to the voxel center. And if both of them satisfy, we will merge them. When there is no more Gaussian, no more partition needed, we will conclude a J high to encode the top 20% large Gaussian at this resolution. The tree plot gives us another comparison between the uniform and adaptive voxelization. Adaptive voxelization is a pure version of uniform voxelization. We set the tau 1 to 5 and keep the maximum resolution the same for both methods. For the voxel contains 5 Gaussian at j equal to 3, adaptive voxelization early stopped the partitioning. For some important Gaussian like the red mark, we always use the highest resolution to quantize. In that case, we not only preserve the rendering quality, but also delete more redundant Gaussian. Here is our compression pipeline. We start from a trained 3D-GS model with the benchmark PSNR. After voxelize it, we have two recolor strategies to recover the rendering quality of a voxelized 3D-GS model. One is to retrain from a point cloud because we discard all other parameters. and we retrain a 3D-GS from a voxelized colored point cloud with low frequency SH coefficient only. So we call it retrain without initialization. The other is just to fine-tune the covariance, color, and opacity of an voxelized 3D-GS. In this process, we pick up the largest volume of the Gaussian in each voxel and average SH coefficient and opacity. And for covariance compression, we have two modes. The lossy mode design a code block based on the relative importance of each Gaussian on the random images and do the vector quantization on those unimportant Gaussian. The lossless compression utilize GPCC and use the predicted lifting transform to compress each dimension of the quadrivium and scaling vector independently, as if there were point cloud intensity. As for color and opacity, for color, we first transform them to the YOV domain in a group of 3 and compress by GPCC configured to ROT. For opacity, we also use ROT, but it's a single channel. And for low frequency, high frequency SH coefficient, and opacity, we have 3 different quantization parameters. The final RD plots generated is essentially based on different combination of these 3 quantization parameters and the selection of covariance compression modes. We compare the RD curve of uniform and adaptive method in terms of the compression performance. We use different partition depths to ensure the number of Gaussian for both methods to make them comparable. After voxelization, we apply the proposed retraining with initialization to fine-tune the remaining parameters. According to the plot, different color are different voxelization method, and different mark are different covariance compression modes. The compression result demonstrates that the blue RD points are better than the green point. This improvement can be attributed to the reduction in the number of Gaussian. In the table, we report B receiving and average PSNR gain using BD rate. The adaptive voxelization saves up to 30% B rate for both scenes and for both covariance compression modes. And for here, we conduct a comprehensive comparison of proposed codec with the state-of-the-art method. The pink points are generative compression. The green points are another hybrid compression method. Red points are post-training compression. For the figure, our method outperforms the post-training method by a large margin, while the generative approach achieves better compression performance, but they lack the ability to compress the model at multiple bit rate. In addition, they require retraining a completely different model for each RD points. These limitations are crucial in practical applications such as the 3D data streaming. In contrast, our proposed hybrid codec enables the generation of multiple RD points with a single fine-tuning process. And our proposed method achieves a performance comparable to another hybrid codec, Mason Gaussian. However, Mason Gaussian requires the fine-tuning at the decoder, which is impractical because it requires to fine-tune at the decoder, and it has to send all the training images at the decoder. As a result, it only generates one single RD point per training. In the conclusion, we mainly contribute to implement GPCC to compress 3D-GS and develop adaptive voxelization for 3D-GS. In the future, we will be working on the ray distortion optimization on 3D-GS compression with point cloud codec, and also integrate the adaptive voxelization algorithm into the 3D-GS optimization process to get a voxelized 3D-GS. And the following link are our code and paper. Thanks for listening.